Good enough. Okay, we're gonna get started. So, we'll start with some information about the test. They all they have had the opportunity to be passed back. If you haven't had them passed back yet and you have lab tomorrow, you'll get that opportunity. They're in the lab room right now. If you want your lab back or your test back, you can email me or any of the lab teachers, lab TAs, and we can get it for you. One thing I noticed is that total scores, last test, people did a lot better on, so if you did worse this test, don't worry about it. More than likely, I don't think he's submitted a corrected, or what's it called? A, like, scaled version. But if you got a lower score on this one than you did on last one, everyone, well, most people did. Last test there's about 20 to 30 A's, and this one there was only 6. So if you didn't get an A, you can get an A next time. I have faith in you guys. 6 A's, yeah. So 90% or above, there are only 6. Yeah.
Do you mean getting half the answers right?
Getting an A of the total score. 90% or above. Without it being, what's that called? Curved. There we go. I couldn't remember that word. I was like, shifting the Gaussian so that the average is 75%. What? Did you take it? Did you take the exam?
I didn't have it until the day. I didn't have it until the proctor.
He wouldn't have taken it. He's a TA. But yeah, maybe everyone else got an A. I don't know. I mean, I do know, but I'm not going to look it up and ask for your names individually. Other than that, yeah, so the average, I would say, this is just by eyeballing it. Last time was in between a 50 and 60% average. This time was probably closer to 40 to 50% average. So it was quite shifted down. Other than that, I mean, that just means that you'll get more points when it's curved, hopefully, right, I guess. So the other thing I want to go over is tutoring. Jason wanted me to cover this real quick. He sent out an announcement. Did everyone get that announcement or see that announcement? There are tutoring hours both in the library, second floor of the library, and then also in the think tank. And you need to make sure that you go when they have a tutor there for Physics 211. And it says every time when a Physics 211 person will be there. So if you need help or if any of your friends need help, you can point them in the direction of that announcement. I wrote down all the individual times, but they should also be on that announcement as well. Did anyone have questions about the tutoring or anything like that? Okay. This is actually going to be a shorter recitation just because you don't have a chapter homework due on Friday, so there's not like a lot to review. But one thing I did want to talk about was conservation of energy, and I want to make sure you guys understand it. So, my markers. Blue. So conservation of energy is, to many physicists, considered the holiest of all laws. This law cannot be broken. This is set in stone. This is what we worship. It's energy. Energy and mass. They're like connected. But this is what physicists believe is kind of the law. This is a very important law. And basically what it says is that all energy throughout the entire universe is conserved. You can't have energy created or destroyed. In the same sense that you can't have mass or matter created or destroyed. It's all tied back to the same law. Now, in simpler terms, that means that if you have an isolated system, you're going to get some total energy, so E tot, and if it's isolated, the change will be 0. Now there's systems where you have an isolated or an unisolated, non-isolated system where energy can actually transfer between other things that you're not thinking about. Today in class, Jason likened it to you can make the assumption that Mars has no sort of influence on your experiment here. So over small time frames and certain assumptions, you can assume that these systems are closed systems, that the energy is not leaving or entering, that you can only worry about the energy in that system. Now, one example of this, so we have kinetic energy and we have potential energy. So the kinetic energy, 1/2 mv squared, it's talking about something moving. It's saying, hey, this thing has energy that's in it. It's not stored at all, it's being used right now. Then you have the potential energy, which usually is associated with U, mgh, so distance that it could change into. So there's a lot of different forms of this. I'm not going to write them all. But just know that potential energy is the form where it's stored energy. It's something that if somehow released, it will move. And that will be converted into kinetic energy. So you have this kind of balance as the system, if it's a repetitive system, like a pendulum or a spring that's in oscillation or a bouncing ball, it will change between kinetic and potential energy, back and forth. Assuming that's isolated and no energy is removed. So the example of a tennis ball that you bounce. Every time you bounce it, it actually loses energy. And you think, oh, well, maybe it's air resistance. So you drop a tennis ball, hits the ground. One thing that's energy is you can hear it hit the ground. It has to give off energy somehow for that sound to be created. It also, many people don't realize this, but compression, if the tennis ball compresses, it actually creates heat. That's also a form of energy. And so every time, if I were to just drop a ball, no way could it bounce higher than what it was released from, if I just drop it. If I throw it down, then I'm actually starting with kinetic energy and potential energy, which means that it can go higher. But if I just start with potential energy, you can never end up with more potential energy than you started out with, because that would be breaking the law of conservation of energy. Now, another example of this is a pendulum. A pendulum is similar to a ball, except it doesn't hit anything. So it doesn't have any energy loss due to compression, heat, sound. Doesn't move. Nothing stops it from moving. It's just the force of gravity that is slowly. In fact, if it was a true closed system, meaning no friction or anything between the rope, no air resistance, it would go on forever. It would just change between kinetic energy and potential energy forever. Just back and forth forever. It still would not ever go higher than where it was dropped from. It can't. You're violating the holiest law. Just remember that every time. You're just like, this is the holiest law. It can't be violated. We can't create energy. We can't destroy energy. Your total initial energy must always equal your total final energy. That's the conservation of energy. Now, I'm willing to put my life on the line for this energy, this conservation of energy law. I'm willing to do it for you guys right now. I have a pendulum right here with a bowling ball attached. It's probably something like 5, 6, 7 kilograms. And I mean, if we really want to know the transfer of kinetic energy, we could, and how much potential energy is transferred into my face as it crushes it. But I have faith that the conservation of energy law is true. So I'm going to try this. And if I die, tell my mom I thought she was kind of cool. Okay. She's kind of cool. She's my favorite mom I've ever had. Do you want to help me? This is going to be my camera. Now, the trick is I can't introduce any energy except for like potential. It has to start with potential. If I tap it a little bit, give it a little shove, when I start it, it will break my face. If I move my face, then I'll change how much distance it needs to travel, and it will break my face. So there's a lot of things I need to do so that this is mildly interesting still. And so I don't know how high I want to do it. I thought about sitting in a chair. But we'll do it so...
Stand a couple rows back. So you swing the whole way. Yeah,
Oh, yeah. Should I do it the whole way?
you want it.
Do you think that will hit anything? Should I do a test run?
Yeah.
Okay. Let's hope that energy isn't introduced via that. I'm assuming that's friction, and the oscillation of it won't do anything. Should I do it on my chin? Okay, you ready? Make sure I don't move. Oh, that's scary. It wouldn't have hit me though if I hadn't moved. Okay, let's try it again. Okay.
Close your
eyes. I can hear it. I know when it's coming. Okay, but that one was probably better, right? Does anyone else want to try it? No? No? Yeah. You want to try it? Come up here. The trick is to not introduce any kinetic energy. Just drop it. Just let it become one with the world.
Pull it back, don't push it forward.
Yeah, and don't move. If anything, move backwards, like I did. Okay.
Something about the four lives back.
Alright. Back a little bit. You lean forward just
Yeah.
Yeah.
One of the issues is that people are like, I'm not going to move, I'm not going to move, I'm not going to move.
you
Boom.
Go into it, but
Yeah.
that would hurt.
Anyone else want to try? This law cannot be broken. It is the holiest of laws. Conservation of energy, you just need to get into your head that this is not English. It's not sometimes Y. It's not, oh, I before E except after C. This will never be broken, ever. Well, as a physicist, I can't say never ever, but our known universe, never. Now, if you go to a different universe, I cannot promise that it will not be broken. Yeah, with a broken face. Be like, I did the bowling ball experiment and it hit me in the face. Okay.
Of course, if you do break it, you better have a decent break.
Better get it on a GoPro, too. So physics works. I'm still alive. Therefore, conservation of energy exists and cannot be broken. No matter how much we try, it can't be. Now the issue you need to remember, though, is this is a closed system. If this was metallic, and we had some sort of magnetic field that introduced another force, that's some other work that's coming into the system. And I would not stand behind a bowling ball that had that system. Now, I didn't do any calculations for the orbit of Mars or the position of the moon. I just assumed that they wouldn't have an effect. And they didn't, I think, for the most part. Okay, so that hopefully gives you an idea of the holy law of conservation of energy. Are there any questions about that? Okay, now so the next part is only homework help, which means that any questions that you have, I'll answer. Do you have a question?
Yeah, so it's pretty obvious when you have motivated by an example like a slingshot, elastic potential energy to kinetic energy. When you have something like a fire, it's like, are you inputting chemical energy or heat or
So
exactly? I guess like what does it do?
chemical is anything that can be described using a chemical equation. So you have, let's just give a simple example. I'm a chem minor and I'm a biophysicist, so I know a little bit more about chemistry. But if you have some sort of carbon, you add oxygen to it. I think it's at the bottom. It does some sort of reaction. So you add heat. And it comes out, CO2 plus carbon again, I think. Or I think maybe it's something. It's whatever the wood left over is. So it's a very generalized form of wood burning. But whenever you can describe a situation using a chemical reaction like this, is a chemical energy. So wood burning is chemical. You are changing the chemical makeup of wood to become something else. And you are changing oxygen into carbon dioxide. I think there was one more chemical equation or question, wasn't there, on the homework? Maybe not.
I think it's still just what does that turn into then? Just the final internal.
So.
I think that chemical energy would become heat and light. Or that, well, I guess I don't know.
Yes, but it doesn't just become that. So the energy, I guess. Let me make sure I'm understanding the question, because I just kind of went over those questions really quick. So I want to make sure I don't give you the wrong answer. Okay. So fire burning. So you have original chemical energy, and then it gets turned into an internal. Yeah, so internal energy, let's see what's the best way to describe it. I think it says here.
I think you described any of these as having an original internal energy and a final internal energy.
I guess, yeah, it is kind of semantics. I don't know.
So why does, like, some of the options on these questions are original internal energy, final internal energy. Like, technically, can't that be true for anything?
Internal kinetic. The only issue that you're dealing with is if it's potential, though, and wood is potential energy. It's available to be burned. It's available to go through this chemical reaction.
Chemical energy is potential energy?
Not in this.
Yeah, not in the sense.
You can talk about potential energy. That's energy available in wood or in whatever that you could extract.
Yeah, have you ever heard of calories? That is a form of potential energy that you eat.
So when it says elastic potential energy, it's
Yeah.
spring.
And so there are different forms of potential energy. So the question where it says, if it were just to say potential energy to kinetic energy, that would be deceiving. Does it say that anywhere? No, the only use of potential energy is in elastic. So everything is stored energy until it's used for some purpose. Yeah.
Okay, so, yeah, my question's on how would transfer of energy work on something like a battery on a cell phone or an iPhone?
That's lithium. So same sort of thing. It's a chemical reaction. I do not know the chemical reaction, but I know it has lithium in it because they always say, with a lithium battery. And it goes over here and becomes, it's going to be some sort of lithium that is a combination of two molecules or two atoms, and then it will change or oxidize, something to that effect. No, I think it's a, I do not know but I know it's a chemical reaction. I just don't know the chemical reaction exactly. I don't know. Ross, do you know?
I don't know lithium, but I mean, traditionally you have a separation between some sort of fluid that has an ionic compound and some other like cavity to figure out if there's a fluid or not. And so you're trading, right? If you can charge it at least, that means you're taking in energy to put it back into the original state. And when it runs, it's using a transfer, so you move stuff to one side electrically. And that causes the
Yeah, the easy example is to think about is a car battery. I mean, that's the one I always think. I think that's the one you were describing, where it has liquids. Lithium's a little weirder because everything's solid in the battery. But with this, you have two rods. Basically, it's divided. You have some solvent here and there, and they're allowed to exchange through here. And so you actually get different compounds when they are using the electricity, and you can charge it and they go back the other way. So it goes back and forth, back and forth. That's chemical. So if you have chemicals, then that is always going to be a chemical. Okay. It will mostly always be a chemical reaction. Yeah.
Can a person jumping onto
Person jumping on a chair.
Like from their muscles?
Yeah, I was trying to think about the muscles. So the muscles don't work as like a rubber band though. They work as contracting. So that I don't think that would be elastic. Why? Is there a question then that's elastic?
It's actually a chemical, is what it says.
A person.
Is the answer chemical?
It is.
I feel like that's a reach, but.
Oh, so that's the kind of the use of glucose to
Yeah.
energy?
Your muscles actually send chemical reactions to work.
Okay.
Yeah.
But that might be confusing.
This angers me.
So I'll give you a hint on that one. I think only one is used on each question. So you have 6 possible answers and 6 questions. You're only going to use one once
No,
each time.
Because 2 of mine are correct and they're the same one.
Oh, really?
B and C.
Oh, C. Oh, yeah. Okay. Dang it. Then which one's not used? The second one? Yeah, the second one's not. Oh, no, the second one is. Second to last. There we go. 5th one. Okay, there you go. There's your hint. The 5th one is not used for any of these questions. Yeah, so sometimes it can be confusing to know which type of energy it is. I don't know if I have a hint on how to differentiate between every thing. I guess you can just really think about how is the energy stored? So you're going from some sort of stored energy state to a kinetic energy state for most of them. There is the car braking to a stop. That's a kinetic to kinetic. Or I guess it's stopping, so it's internal. But it does start as a kinetic. So for most, they're transferring between some sort of kinetic to potential or potential to kinetic. Because you have to conserve energy, so it can't go anywhere else but potential. So if you're losing kinetic, it has to go potential. If you're losing potential, it has to go kinetic. I'm going to say 99.9% of the time, because I never say always, because that's always difficult. Yeah?
So I was wondering if you could clarify question 2. It says that you've got somebody who decides to drop a bowling ball off the building, and you've also got somebody at the bottom of the building, observing the.
Yeah. So it asks you, you have 2 reference frames, and it asks you what do they share in. True, but they have different values. Let me give you an example. If I'm on Mount Everest, do I have the same exact reference frame as I would have here? What's changed? Your height. But what does that change with respect to potential energy? What is potential energy? What changes in this equation if I'm on Mount Everest as opposed to here? There's one variable. You can't change mass, you can't change height. Gravity. So if I drop something on Mount Everest, it's going to have a different potential energy than if I drop something somewhere else. So in this,
The thing that they are focused on more is that if you change your 0 point to be the top of Mount Everest while you're over there, then the way you measure potential energy is going to be different than if you fall 0 height.
that's true. You would have,
Here in Moscow.
So
it would be negative instead of
Yeah.
when
positive.
looking at
or-
the entire ball Earth system though, would they say that the value is different if you're seeing it as positive or negative? Is that what they're looking for? Because I don't understand how that's not right.
So the value of the gravitational potential energy of the ball Earth system.
I don't see how
They're
it's
doing
they are doing
with
that.
energies, positive and negative make a difference.
Okay.
That was kind of confusing, so I
The
agreed with
ball.
the magnitude question for the screen.
Uh-huh.
I took the equivalent classes, that meant you better give me a positive number, whereas Jason would be a little more lenient with that. But with energy, it does matter, especially when you, not in this class, but you get attraction, repulsion, positive and negative mean different things.
So you're saying that the person at the top of the building assumes that they're dropping from a 0, and the person at the bottom assumes that they are the 0, and it's dropping from a height x. So the person is dropping from 0 to negative x, whereas the person on the ground is seeing it drop from x to 0. Is that what you're saying? Okay. Which would introduce a different sign.
Which would also be the same for kinetic energy, because assuming one would see negative velocity. Okay?
Well, think about kinetic energy squared velocity. So you're going
So
to go away.
so it has to be.
So that's the gravitational potential. But yes, there are different circumstances where you can set up the equation. And one of the,
The kinetic energy has to still be different.
But for both people, we see the same amount of time.
yes, so the kinetic energy should be the same.
Is the change in potential energy always have to be positive? Is that considered solely magnitude?
The change in potential energy?
So these changes are much more like displacements, where it doesn't matter what your reference is, and that determines the sign of your changes.
But they should agree on the kinetic energy as well. Yeah?
So both of them should have the same final velocity.
It's really easy if you actually try to do a simple like change, and you literally do the guy at the top and the guy at the bottom.
Well, it's saying like at some point, it's like halfway down, they're both going to agree on the mass and the velocity. Well, at least the point that the velocity squared.
Yeah.
They just have got this problem on it.
Let's look at it.
I would suggest, honestly, like, the worst thing is to keep answering it. It's really good to write something out, try to write out your thoughts, try to talk to somebody about it, and then maybe like I'm pretty positive, like you want to be able to say like I have this much certainty without even entering my answers, right? Because otherwise you're going to be flipped on something, you're not going to track your little mistakes.
Hmm.
But if the change can be positive or negative,
You're going to want to write it out and see what it is. You don't want to say it can be or it can't be. So like Kyle said, if you call the height of building X or H or whatever you want to call it, you can give a regular number if you want. And you say what's the change for both people. So this guy's reference what is the change equal to? This other guy's reference what would you say the change equal to? Whatever the signs are, compare them.
Yeah.
So, right, you can say energy before equals energy after. You can say, what would this guy call energy before? What would this guy call energy after? And then if you look at just the potential energies, you can say here's what the change is. The change is the final minus the potential after. This is the definition of change in anything. What it is after is what it is before.
That's a hard concept. If it helps, gravitational potential energy is big G mass X. I believe this is negative. Where G and M are gravitational constant of the planet, M is the mass of the Earth, and X is the distance away from the center of the Earth. This is defined as V, which is defined as your gravitational potential energy. So by changing X, you change, which is the first one, the value of gravitational potential energy of the Baller system. You will have a different V. which is why the first answer is not correct. Hopefully that makes sense. Okay.
Problems are sometimes ridiculously overcomplicated and stuff like that.
Yes, in fact, sometimes I go to Jason and I say, hey, even I got this wrong, so you should like throw this one out. I did that for one homework assignment. No, he didn't throw it out. I just gave you the guys the value for K or something like that. And he just put it on the home, and then it was just like a plug and chug.
I think this question is way better than the first one.
Yes, the first one is kind of,
For an example of something that Jason would want to kind of test you on, I would say the second one is like something you're more likely to try to do this analysis for.
yeah, I think you're right.
He went over energy before energy after, and then you can always look at any change. Well, I mean, any change in is thought of as something final minus what it was before, and that'll get you the right sign for that reference.
Yeah, so, well, I can see him doing something similar to 2, though, for a multiple choice question. Both of them, actually. I could see him doing both of them for multiple choice, which makes it that much more necessary to find out why everything is that way. Yeah, I mean, the only one, I mean, there's some that you can rule out instantly, but I mean, the main thing you need to do is just sit down, look at what the energy source is. So identify potential, identify kinetic of every single system. And if you identify the potential and the kinetic, you should be able to hopefully deduce which one is correct. And then as far as the second one, you should just write down everything. So kinetic energy of the ball is this. Potential energy is this change in x. Same, different. So change of potential energy is the same. Kinetic energy of the ball at some point in his motion is the same, but that one is not. Okay, are there any other questions? I mean, there's only 2 questions, so I think I've answered them both fairly thoroughly. Any other comments, concerns? Okay, we'll go ahead and end recitation. Send, or go to the communication with your teacher, or ask for help thing, and Ross will answer it, because that's what he does now. And if you do have any questions, you can email me, I guess, or anything else. Okay, well, thanks for coming, and I'll see you guys next week.